Saudações.
And welcome to Context Free, where we talk about programming languages. Today, I want to talk about async await in some systems programming languages, specifically Rust, C++20, and Zig. They have some things in common and some differences in how they do things. And I don't just want to talk about how we use async await, but also how you might implement your own event loop, or executor, or scheduler, or whatever you want to call it, that makes the async await happen behind the scenes.
The compiler creates the coroutines, but someone's still got to run them.
Let's get started with Rust. Here we have a simple program with an async main that awaits our run, and our run awaits two calls to count. All three of these are marked async. So what is async? For these languages, we're talking about coroutines, where you can say, please, for example, sleep and get back to me later. The execution of this function is suspended, and other functions can run instead. And that may or may not be on different threads. Might also call this cooperative multitasking in a way. And today, I'm just looking at sleep. Sometimes you might care about sleeping in an asynchronous fashion. This could also be proxy for doing a web request or some background computation. So again, in run, we call count twice, and we'll count till 2 with 1 second sleep before each, and we'll count 3 times with 0.6 seconds between each. Here's our loop, and there's our sleep. We report after each sleep. And just so we can see how return values work, we'll also return the amount of time slept in this function. Then we'll sum up the time slept, although if the counts are happening simultaneously, then the total time slept independently is not going to be the same as the simultaneous wait that we have going on here, joining and awaiting on these features. We'll return the total anyway and report that at the end. Let's see it in action. And here we see our sleeps. I also print out the thread ID, in this case proving that while these things are happening simultaneously, they're all on the same thread. And for my async framework today in Rust, I'm using async standard, which is not part of the standard library in Rust, but rather implements portions of the standard library in an async fashion. Tokio is another popular async framework for Rust. Now notice here, when I say begin, then before loop, then sleep. And after I call this function twice, then I print count size. But if we look over here, we'll see begin and count size before the before loop printouts, showing that even though I had called these functions, they had not started executing until I awaited them. But the end print does occur after all the sleeps. And we waited for 1, 2, plus 1.8, or 3.8 seconds total, but finished our execution in 2 seconds because these sleeps were happening simultaneously. Now in Rust, main by default doesn't do async. Instead I've used this macro from async stood. For kicks, let's take that away and use a main that's synchronous instead. Here I've said run and stored the future. Then I call async stood's block on to get the result. Let me print this out. Acts the same as before. Also notice that I'm printing out the sizes of my futures, either the size of one of my counts or the size of this run call. Count was 176 bytes. We can think of the variables here as being sort of like a struct. It has to maintain the state while the execution is pending. And just to prove there's a relationship, let's change the usize to U128 and run this again. Now we see that the count size is 200, so the previous 176. Whatever's happening internally ended up increasing the size of this future by 24 bytes. Let's go back to the usize. And let's go on to C++. The C++ standard library, just like Rust, doesn't include an event loop, or whatever you want to call it. So I've used a third-party one here called Kuro. The author of Kuro doesn't recommend using it in production, but I found it much easier to use than some of the other alternatives. And like the synchronous version of Rust's main, I have a main here also that's synchronous. So I'm going to explicitly run and wait for my task, which calls count twice again. And Kuro gather is like the join all from Rust, except I pass them in as variadic arguments rather than having a collection of them. And we use prefix co-await instead of the postfix await of Rust. And instead of return from our coroutine, we co-return. We also don't mark our functions async, rather we mark that they return a task. And what constitutes a task? We'll get to that later when we look behind the scenes. Let's just run it for now. We see the same behavior as before, including count size happening before the before loops, although it's only 8 bytes here. In my C++ demos, all I see is a pointer rather than the full structured data, but we might look slightly behind the scenes later. Before doing that, let's look at another implementation in C++20. This uses libunifx, which is one of 2 async frameworks under development at Facebook, and one of the widely recommended frameworks for more serious async work in C++20. But I find it much more complicated to use than Rust or Kuro. One of the differences for Unifx is that you choose what kind of context you want to run your schedulers in, and they're not 100% compatible with each other. Although by using a template on our scheduler, you get some level of compatibility across them, and they nicely have some amount of concept enforcement here. And one of the key differences from Rust is, at least for how I found to use it, you pass your scheduler in to your calls, so that even down here where I'm sleeping, the scheduler comes in and is able to receive the task for execution. There's also a bunch of variant and option wrapping that happens, making it a little awkward to get your results out. But by and large, it works the same. And I can even swap out this timed single thread context for an epoll context that has extra cleanup work to do and also requires a slightly different call for scheduling a task, or sleeping in this case. Worth pointing out that in my previous context, I actually had my sleeps and my end come back on a different thread than where I started and where I finished. And on epoll, we see the same thing,
although that's dependent on the specific implementation in Unifx.
And I'll point out that epoll is a standard in Linux at the operating system level for managing events, including network events or timers or so on. On Mac, you'll use KQ, and on Windows, you'll use IOCP. And you can make executors or event loops that integrate with different back-end event loops depending on your platform. Let's move on to Zig, which feels different from Rust and C++. Here in main, again, no reference to async. I just call run and report the total. Run also doesn't say async, but when it calls count, we at the call site say that it's async. Then we wait for them in a loop. And up here in our count, we use a standard sleep, call sleep without referencing async or await, and return the time elapsed. So again, in Zig, you emphasize at the call site if you want to deal with something in an async fashion. And by default, a call will be considered sync, meaning it does the async and the await automatically. Let's run this. We see all my code is executed on a single thread. In this case, we see before loop called before we get the count size out, because your async functions always kick off immediately in Zig until something that causes them to suspend. And just like in Rust, we see the size of our frame, and you just call them frames in Zig as well. And the standard sleep just calls into the singleton event loop sleep. We also had a singleton behind the scenes in Kuro. So if I didn't care about doing async, this would just feel like a sleep that was synchronous instead. And to emphasize this issue of you can async and await anything, let's call some random silly function here and prove that this works. I have asynchronously called hi, then awaited the finish, which is somewhat useless because nothing in here will suspend anyway. Await just means wait until this frame finishes, which it will have done instantly. No change in behavior from before. Still 2 seconds total with 3.8 seconds internally. And while they're looking into redesigning the standard event loop in Zig, I'm using what they have at the moment, which is built into the standard library and uses things like epoll, KQ, and IOCP behind the scenes. So now let's see what happens if we want to implement our own event loop in Zig, which I've done right here. And this is a super simple event loop that simply actually just waits in a busy loop for sleep times to expire. In my sleep, I will suspend the execution, find a slot for a task, which just stores the frame that needs run and the time that the sleep expires, calculated right here, and it stuffs this task into that slot in the very limited task list. Again, the point is to see how things work behind the scenes, not to implement a solid event loop. The loop itself loops through events. If it finds a task, it sees that the time's over, provides that finished frame, resumes the frame, and then quits if we run out of tasks. So let's swap out the standard sleep for my sleep and also kick off my event loop processor ahead of time in a separate thread. Here we see the same total effect, but with my sleep over y'all call that happens right here. We also see a change of thread right about here from 47 to 57 because I've kicked off this event loop in a separate thread. The thread that resumes things is the thread that picks up execution over here. We saw a bit of multiple threads in C++ earlier, and Rust can do that as well, depending on the executor. I could also run this event loop in the same thread, but because of how I implemented it, I need to have my events queued up before I start the loop, and then I can await it when it's done. Where I've gone from the apparent synchronous call to splitting the async and await. In this case, since I didn't run it in a separate thread, everything's all happening on a single thread. And when you're doing async and zig, do take a look at this pub_const io mode equals .evented. This is how you signal that you want your main to be async and that you want access to the event loop should you be interested. Zig is able to look at the root source file and ask things about it. You can do this in your own code as well. So having seen a custom event loop in Zig, let's look at one in C++, where I will hide the real Kuro and make a fake Kuro instead. Although I sadly failed to implement a fully working example in C++.
In the time I chose to spend on it.
There's lots of moving parts, which we'll see in a second. So one thing my implementation can't do is two tasks at the same time, which makes it rather useless. So I don't recommend using my framework for your async tasks. Actually, for any of these languages today.
My implementations are just for learning the basics.
So we'll just await a single one of these. And work from there. These squigglies are yelling at me. We'll see if that's a real issue or just an editor problem in a second. Let's see if I did this right. Sweet. I'm all on a single thread here, which is running inside of this fake Kuro event loop run. And I see looping over events y'all and the sleep being over for my single task this time instead of multiple. Also, if you notice, we switched from count size then before loop to before loop first, because in my implementation, the coroutines kick off instantly. These are all configurable. And to remind ourselves of some concepts, let's look at the Zig here again, where we had things like suspend and resume. We'll see similar notions in our C++ implementation. And again, as I mentioned before, you return tasks from asynchronous functions. What's a task look like? It looks like this. I can name a task whatever I want, but I have to have a promise type inside of it that's named promise_type. There's a whole lot of duck typing that happens here in C++ 20 coroutines. This promise type is required to have things like getReturnObject, final suspend, initial suspend, unhandled exception, and either return value or return void. And since in my implementation initial suspend does suspend never, that's why it kicks off immediately. Now as for the sleep function, I create a sleep awaitable, again calculating when the time expires and returning this thing for use elsewhere. Anything you can co-await has to have an await ready, await resume, and await suspend. Ready gets called first to see if it should sleep at all. If it should suspend, then await suspend gets called. And in this case, I store that task onto my task list. And resume is sitting here as an event handler in case you care. In this case, I don't. Just like I had an array in Zig, I make a std vector in C++, where I have the thing that needs resumed and when it's done. And that's what my event loop handles down here. Very similar, really, to the Zig implementation. While I have tasks to work on, loop through the tasks, find if one's done. If so, clear it out, tell it to resume, and go back to my outer loop. When I'm all done, clean up the root task and return my return value. Note what I'm resuming here is a coroutine handle. So we have tasks, which you return from asynchronous functions. You have awaitables that you can co-await. And actually, if you don't want to have a co-awaitable object directly, you can actually have an operator co-await that returns you one. And the actual things themselves that suspend and resume are the coroutine handles. As I said, lots of moving parts. Now furthermore, in our task here, in order to make it awaitable, so you can have nested tasks, you have to have the proper await handlers, which again are duck typed. It expects to find certain functions with certain conventions in order to use these.
Although you can define concepts for them if you want.
And the final suspend in this case can fall back out to a parent task for the nested tasks, which we see here that count returns a task, then Kuro re-awaits on that and sends it out. These are the nested tasks I'm referring to. I have at least one other bug in my C++ implementation as well. Let's run this through Valgrind. We see here that I failed to clean up all of my coroutines. 112 bytes lost. Let's put in that leak check equals full. And we see that these 112 lost bytes were allocated in function count at line 27 over here. So we can see how big our task was and that we failed to free the memory. It was allocated by operator new, which you can overload as you see fit. So having seen this code in C++, let's get back to Rust. Pop our stack back to the beginning. So here's how we handle our sleep in Rust. We create a future which implements the future trait. Let's review our code again and prove we can run our own version. Instead of async standard, let's use my exec instead. And instead of the async stood block on, let's use my block on. Let's see how this goes. Acts like before, 3.8 seconds internally, 2 seconds total. We see that my looping events and sleeping is happening, and on different threads. For C++ 20, I recommend this blog post from Jeremy Ong, aka 9 Points. And for Rust, I recommend the Async book, which includes sections on building your own executor. For Zig, it has some assistance from maintainers. But for the Rust case, I took this almost wholesale from the Async book. And one difference it has from the Zig and C++ implementations that I made is that instead of a busy wait loop, it instead spawns a thread to sleep and then notifies the loop that it's ready to go. So the event loop or executor is going to be running on the main thread, and background threads are doing the sleeping. So here's my run. It waits for tasks from a queue, gets the future out, polls the future to see if it's ready, then either continues to wait or returns the result. And one of the key things that's happening here is the passing in of a waker into the future itself. This is the way the back and forth communication happens. Because in Rust, when I said await, I didn't tell it what event loop to use, and I'm also not using a singleton. It sneaks in behind the scenes into the future, even though it's not visible in the function call. It's almost like dynamic scoping of a sort. Over here where we first create the sleep, we don't have that waker yet. It only becomes available when poll gets called, the context comes in, and we get the waker from that. We put that into the shared state, which is atomically reference counted and usable across threads, so that we can get the waker from our shared state and wake it up to let it know when we're ready. And so because of this standard of wakers and future trait, I can make futures that are compatible with other event loops. So I can even mix and match. I can use the async stood sleep with my event loop. We see my event loop, but not my sleep messages. Or you can use my sleep with async stoods block on. Where we see no waiting for events, like up here, but we do see my sleep messages from the separate threads. And in fact, we can use both from the same program, where first I'll block using my loop, and then I'll block using theirs. But I'll use the standard sleep to make it quieter. Looping events, y'all, but down here not. Worth pointing out that there's ways in Zig to integrate with the standard event loop as well, and presumably there are in the various async frameworks for C++ 20. Anyway, I hope this has been fun. Maybe we can look more at coroutines of various sorts in the future. If you like the video, be sure to subscribe.
Até mais.